All right, people. Today we are going to be talking about real gases and the van der Waals equation. Now, I'm sure I'm mispronouncing walls. It might be balls or whatever. I don't know what it's called, but whatever. It's important. Now, we're not going to do any calculations with it because it's difficult. That's honestly why it's difficult. I've done a few calculations with it in PChem a while ago, but I haven't seen it since. You won't see it. You need to know about it. All right. Now, before we even talk about real gases, let's look at the ideal gas law. The ideal gas law is the relationship between pressure, volume, temperature, and the number of moles. And the ideal gas law follows the kinetic molecular theory. It follows the four postulates I have underneath. And when we talked about the kinetic molecular theory, I said that this one was a little bit off. The assumption that the volume of individual particles can be assumed to be negligible, to be zero, it is wrong. It is wrong, and that assumption only works in certain conditions, but majority of the time that fails. Now, let's say it completely fails. Which variable is it going to affect the most? Well, gases take up the volume of their container. So if you have a container and it's full of gases, right? Since we follow the kinetic molecular theory, well, there's no gases taking up that space. But in reality, these gases take up their own space. So the space of the container is now reduced. So this V needs a modification to it to account for that. We have to actually change our equation so that it represents the available volume. The volume, but now taking into consideration that the gas particles actually have take up some space. So if we look at this, wait, this is not the right one. Let's get rid of this one. This right here is now what the new gas law looks like. It's volume minus, and this NB, just think of it as a number that represents the amount of space the gas particle takes up. So remember, gas particles, we said they're tiny little dots that don't take up any space, but in reality, they take up space. They take up space. So you add that NB, and the B is really what accounts for the space they take up. The letter N is, again, moles. The more moles you have, the greater the effect on the container. If you have almost no particles, then B is going to be very, very small. So your gas is going to be ideal. If you have a bunch of particles, then this number is going to be very, very big, and it's actually going to affect that V value. For some reason, I want to call it V value. The V value. So N is the number of moles, and B is the variable that accounts for the space an atom takes up. So this is one way that van der Waals accounted, or van der Waals accounted for a real gas. But that's only one portion of it. The second portion that we mentioned was on, number 3. We said that the particles are assumed to exert no forces on each other, and they don't attract or repel each other. So let's take that over here. Oops, don't get scared. Don't get scared. I got scared. Let's pretend none of that is there. Let's sweep it under the rug. Hide. There we go. Oof, much better. Now, imagine a particle. Oh, I'm going to move this over here. Imagine a particle crashing into a wall. Now, on its way to the wall, all these dudes, all these people all these particles are attracting that particle. So they're actually going to weaken the force it applies on the wall. So it's actually going to lower the pressure. It's going to change the P value. And if you had way more particles attracting it, say you had a bunch of particles, well, now they're pulling it back, so the pressure is going to be affected even greater. So the number of moles is going to affect the amount of pressure. So that means that we have to make some correction to the p variable if we want to show a real gas. So let's get rid of this one, because now let's show the correction. So this right here is now the correction of the pressure. So this value right here, that A and then N over V is the correction. And once again, N is the number of moles. And then A is a number that corresponds to the type of gas, because some gas particles will attract each other more than others will. So there's a table over here that has the A values for all the different types of gases. And if you take a look at NH3 and H2O, their A value is really big because they have attractions. They have some very, very strong attractions that is going to drastically change the pressure. If you remember NH3 from a video a while ago, when we talked about the molar volume, we said that 1 mole of NH3 wasn't 22.4, it was like 22.2. So that attraction actually changed the volume. So that A has a great effect on this gas. It doesn't behave like an ideal gas. Helium behaves like an ideal gas, and neon behaves like an ideal gas because those values are so small. All right, now the more particles you have, the bigger your N, the greater the effect on pressure it's going to have. So you don't have to memorize this equation, but this equation does help explain the corrections and the issues with the kinetic molecular theory. All right, so we can actually rearrange this equation. Now it looks like we can barely recognize it, but if you move the correction factor to the left, then and you basically move your volume to the other side, this equation now looks a little bit more familiar. This is pressure, but now it's the pressure accounting for this interaction. All right, so that's basically what our P used to be. And then this volume, well, now it takes account for the size of the atom and the number of atoms. So that's our V, and then on the right is nRT. So the ideal gas law with some modifications and a little bit of further studying, right, shows a new model that can be applied to a bunch of different gases. And one, it's very complicated, but two, it's very, very useful because now it explains discrepancies. It explains why NH3, well, it shows that NH3 has a lot of attractions. So we're going to talk about why it has those attractions. Where do they come from? It's a very, very important topic, okay? So keep that in mind. But this is the van der Waals equation. This is, yeah, hopefully this makes sense. Don't get too scared off. I'm not going to have you do calculations with this, but I do need you to understand what the corrections are. So what's the correction here, and what's this correction for? What are they accounting for? All right, and that's basically it. Peace out, people. Take it easy.